Yeah.
Yes, yes. No issue. Can we start now?
Yes, madam, I am ready.
Okay.
Yeah.
So once again, good morning to you all. Good morning to Dr. Ramsha Karampuri and all the participants to session 14, which is the last session of this FDP. I'll give a brief introduction about Dr. Ramsha Karampuri. Dr. Ramsha Karampuri completed his PhD from NIT Warangal in 2019. He has 12 years of teaching and research experience at various institutions, including University of Sevilla, Spain. He has many journal and conference papers, 1 book chapter, and 2 patents to his credit. Currently, he is working as assistant professor in the Department of Electrical Engineering, Visvesvaraya National Institute of Technology, Nagpur, Maharashtra. Dr. Ramsha received the prestigious Heritage Fellowship under Erasmus Mundus India-Europe Exchange Mobility Program sponsored by the European Union. He received an esteemed invitation from Rashtrapati Bhavan, India for participation in the batch of NIT's Scholars in Residence program at Rashtrapati Bhavan, New Delhi, where he got an opportunity to meet and talk with Honorable President of India, Sri Pranab Mukherjee. Dr. Ramsha has received many best paper awards and he is the reviewer of interactions on power electronics, transportation electrification, vehicular technology, Journal of Emerging and Selected Topics in Power Electronics and various other journals. Thank you for joining us in our FDP, and now you can start your session. Over to you, sir.
Yeah. Thank you, madam. Thank you for introducing me, and thank you for giving me the opportunity to share my ideas in this FDP. And yeah, to start with, just I am here to share my experience, rather not giving you like any research updates, or just I want to share my research experience where I have faced a few problems while implementing some controller in my research work. So basically, in this session, I just want to discuss in depth like how a research problem can be like how it can be viewed and how we can rectify the problem when it arises. So in that context, I just want to talk regarding the implementation issues of power electronic systems in digital signal processors. Right. So I once again thank the organizers for inviting me to this FDP. Yeah, let us start. Yeah, like in between, if someone have any query, there is no issue with me. You can interrupt me, and we can have a healthy discussion because it's not. I just don't want to have a lecture in only one way. If it is a two-way communication, it would be better even for me. So I have no issues in discussing in between, right? So, or else, if someone hesitates to talk, you can share it in the, I think, maybe Q&A section, so that we can take it at the end. Okay. Yeah, madam, may I know till what time can I continue?
90 minutes session and 30 minutes question and answer session.
Okay, okay. Okay then.
1 to 1:30 question and answer session. Yeah.
Yes, yes.
Yeah.
Okay, so to start with, as I said, I just want to share my research experience where we face some problem during my research. So my research has focused on PV fed water pumping system basically. So PV fed water pumping system. And here we have proposed for the first time, we have proposed open and winding induction motor drive as a single stage system. That is, we do not have any like DC-DC converters in between. Directly with the inverter connected to PV system, we try to work out with the water pump, like three-phase open and winding induction motor coupled to a centrifugal pump. Okay, so this was the like major theme of our research, and in this we try to propose few PWM techniques which can eliminate like even common mode current, and also to implement MPPT. So we have proposed some integrated control algorithm. So this was like integrated control algorithm where it integrates PWM technique and also MPPT technique and even open loop VBIF control. So three controllers in a single implemented using a single controller. Three controls implemented in a single controller. So this was this task, and using this controller we need to generate firing pulses for both the inverters, that is a dual inverter. So as I think a few of you might not have any idea about open and winding induction motor drive, just in short I'll tell what is this. You might have done many people might have done on a conventional three-phase induction motor, so which is having a short circuit at the other end of the stator winding. Okay, so A, B, C, these are the three phases given to the induction motor, conventional one with a star connected at the other end. So this is the conventional one, but rather if we use open and winding induction motor, there are many advantages over this. So basically, like, we can reduce the DC link bus voltage and thereby reducing the size of the capacitors, and we can reduce the size of the power electronic switches, so and on. And also it has proved to be a like economic system when you compare with a multi-level inverter fed induction motor drive. So that we have already published. However, an open and winding induction motor is formed by opening this end, which was short circuited, just taking out all these 6 leads out from the three-phase winding. So you have 6 terminals out from the induction motor stator winding. So this is how we call it as a open end winding induction motor. It is open end winding. So winding has 2 open ends. Okay. So either of the side there is no short circuit. So we can pump power from both the ends using these 2 inverters, and these 2 inverters we in general call it as a single inverter, as dual inverter. So it is a dual inverter configuration which is connected to open and winding induction motor drive, and which can give you directly 3-level output voltage. Okay, because this is a 2-level inverter, this is again a 2-level H-bridge inverter, but combinedly in a combination, if you see, the dual inverter gives you 3-level output voltage. Okay, so basically this is the system description what we had, and also I said that these 3 tasks should be accomplished by using a single controller which can operate or which can generate the gate pulses to these 2 inverters. So gate pulses in general will generate for like 6 switches of inverter 1 and 6 switches of inverter 2. So in total we may have 12 gate pulses which can be generated from the controller. Or one more option we have, like we can generate only 6 gate pulses. So for top switches like S1, S3, S5 and S1 prime, S3 prime and S5 prime. So for all these top 6 switches, if we generate the gate pulses, it is more than sufficient because the bottom switches are exactly complementary to these. So S4 prime is complementary to S1 prime and so on. So all the bottom device gate pulses can be generated by just by using a NOT gate, so that we can have complementary gate pulse, and yeah, of course we may have dead band inserted in it. So dead time we shall have in between top and bottom pulses. So this is the overall description of the system. So as I said, in this system we do not get much difficulty because when we try to implement the MPPT along with some PWM technique and as well as VBIF control, open loop VBIF control. So we just need 2 sensors, like one is for measuring VPV across solar PV system and other is IPV, which can be sensed by using current sensor, and this is by voltage transducer. So this can be given directly to ADCs of your controller. So we need only 2 ADCs, so which can convert these analog signals from the sensor into digital and give it to your controller. So that MPPT technique will be deciding or defining your modulation index for the PWM technique, and also we can give the DC link voltage we need for any PWM algorithm. So that DC link voltage as well as modulation index is being given to that, and then it is processed to generate these gating pulses, and which should be given to IO pins of your controller. So these IO pins, like generally named as GPIOs, general purpose IOs we have in the controller. So that GPIOs will be providing or giving you as a dedicated EPWM pins. So generally few controllers has only PWM pins, few controllers have EPWM pins. Okay, anyhow, I'll be explaining what is the major difference between a PWM pin, EPWM pin, and specifically a few may have HR PWM pins. So they may also have high resolution PWM pins. So this difference I'll just try to explain in further slides. So for time being, just remember that we need to give these gate pulses switches gate terminal of the switches, so which may have in between gate driver circuit. So controller GPIO pins are directly connected to your gate driver circuit, and output of your gate driver circuit is given to your gate of the switches. So maybe here IGBT, or you may use MOSFET for some other converters, so which can be given to the gate of the power electronic devices. So for this purpose, actually, initially we had a DSP controller with us. So using this DSP controller, we do not much have any complexity in it because the program and all, it is very simple to implement in DSP controller. The same MATLAB Simulink file, whatever we have, the MATLAB model, that can be dumped directly into the DSP, and it can inside it you have like FPGA as well as DSP processors. So these will be taking care of like implementing the control algorithm, whatever we have in MATLAB program, that can be directly dumped into these processors, and it can generate the gate pulses. So this we do not have any much issue. So that we had implemented it like with the ease. So this is the experimental setup what we had to implement the system which I have shown you earlier. So in this system you can see it clearly, like you have a rectifier output, that is DC link voltage has been generated here. So this is your DC source, and yeah, this is your DSP. So DSP controller, which has been implemented to run this 3-phase open and winding induction motor drive, for pumping application, because as here you can see a fan type of load which is parabolic load, which is similar to the centrifugal pump, which can emulate centrifugal pump here, and this DC source is emulating your PV. So PV is emulated by DC source and pump is emulated by your fan. Okay, and these are the inverters, two inverters, that is dual inverter, and then these are your gate driver circuits, so which are applied to the switches. So controller output is given to the gate driver circuit, and gate driver output is now going to your inverter. So controller to gate driver circuit, and from here to inverter. So this is the overall system that we had for a three-phase open and winding induction motor drive. Okay, so successfully we have implemented it, and the results we have published already in like 2 IEEE transactions. That is fine, but when we try to extend our work to let us say 5-phase machine, we have interested in extending our work to 5-phase machine. Not a simple 5-phase induction motor drive, but it is again 5-phase open and winding induction motor drive. This application we have mainly focused it on, say, electric vehicle. So for electric vehicle applications, when we extend this 3-phase open and winding concept to 5-phase, and specifically if we go with electric vehicle, maybe like we should have some closed loop control, closed loop speed control. Okay, maybe like you may have DTC or PTC or MPC. There are many controllers now, closed loop control schemes you have. So any of the control we may have. So we just want to extend our work to this. Okay. So in that case, yeah, this is the system what we had. The same PV fed 5-phase open and winding induction motor drive, and which can have similar control. But now here, if we want to extend it to 5 number of phases with a open and winding configuration, we have total 10 legs in 5-phase dual inverter. This is now 5-phase dual inverter. So you have 10 legs in total and 20 power electronic devices you have. So in previous case there were only 6 and 6, 12 devices, and for 12 devices you may generate only 6 pulses, 6 gate pulses, and apply NOT to them, so that you will get other 6 gate pulses, so that 12 switches can be operated easily. But here now we had an issue in implementing the hardware, because the DSP system which we use, it has its own limitations. Even with the switching frequency, we had limitations with the DSP. So now we thought of implementing this 5-phase dual inverter system, and this same controller. Actually, this control technique will also get changed. Actually, it should handle all the 5-phase signals. In previous case, it should handle only 3-phase signals, but here it should handle 5-phase signals. And 5-phase signals for both the inverters, like it will be doubled, 10 signals it should handle. And again, same MPPT controller with some phase displays PWM technique along with VWAP control. Let us say simple open loop control. Then we have extended closed loop control later on. But the same control technique, if we wish to extend it to 5-phase open and winding induction motor drive, the major problem what we faced is we need to generate at least 10 PWM signals from a controller. 10 PWM signals from a single controller. Right. So by approaching various persons from like various places and various institutions, we got few ideas, like saying you can have a master slave kind of processor. So like you connect it as a master and slave. So from master processor you generate 5 pulses independently, and from slave processor you generate 5 pulses independently. So this was one of the options or one of the solutions given to us by various experts from various institutions and research centers. Like, I don't know, we do not get satisfied with this kind of work. Like, why to increase the controller size and controller extra controller, if we include that, will increase the cost of our system. And also synchronizing these two controllers is again a major issue, because it should be synchronized even with like even at higher frequencies. Maybe in few nanoseconds or few microseconds it should be very well operated. Otherwise, if it is differing in microseconds, if this inverter firing pulses and this inverter firing pulses, if they are differing in even in few microseconds, then you may have circulating currents in this inverter, in this dual inverter, because as we are using a single DC link for both the inverters, it would result in circulating currents which may flow through these inverter switches. So if you do not maintain proper dead time between the switches, and if you do not maintain proper phase shift in between these two inverters, then it will result in circulating current. This is one of the technical issue, and like economically, if we use two converters, then it would increase the cost of your system. So based on these reasons, like, we are thinking like what should be done. So since whatever the processor or controller we are talking about, that was having mostly, you may have 6 channels of PWM signals. So those 6 channels means independently you can generate 6 firing pulses actually. So this was the major issue what we are facing about. So let us see how we have solved that issue, how from where we got the solution and all. Let me discuss and disclose it to you. Okay, so before disclosing, let me show you our experimental test rig what we have developed in our lab for implementing this 5-phase dual inverter, because even construction of this inverter is again a challenging task, because in Indian market, like directly, we do not have any 5-phase inverters available. They should be custom made. So if we consider a custom made inverter, it would charge you a lot. Like, as we have inquired, for a conventional 3-phase inverter which was readily available, it may cost you around mostly like 30,000 or 40,000. But if you want to make a custom made inverter like this, like 5-phase and all, so they may charge you around 80,000 to 1 lakh rupees. So this was the variation in the pricing of inverters. So we thought of like why to rely on the company where they charge more for us. So just we want to make our own inverter. So this was the inverter which we made in our lab. It is indigenous inverter, completely made by us in the laboratory. So it has these gate drive circuits. So yeah, these are the gate driver circuits. So 4 gate driver circuits you can see for top switches and bottom switches separately for 2 inverters. So these are the 2 inverters in between. So with the red and blue wires you can see 5 phases there, and DC link capacitors and logic power supply also you can see in this. So yeah, here you are getting input from controller to the gate drive circuits. Okay, and these terminals are your output. Okay, so 5 phases we have taken from there. So this is a custom made inverter what we have implemented, but this is not a like big challenging task for us, but challenging task is implementing the program in the controller. So yeah, this is the overall setup for experimentation for operating this 5-phase inverter. So this is a DC link DC bus voltage which we have given through programmable supply, and You can see here, this is the main important part of our session now. This is your digital signal processor, where we have implemented the control program for controlling the 5-phase dual inverter. Okay. So this is your 5-phase open and winding induction motor, which is again a custom made one. Okay. So let me tell you the solution, how we have made it. But before going to solution, let us have a brief introduction about the processor, because in the process, when we started thinking of implementing our controller for 5-phase dual inverter, what exactly the problems faced and how we have proceeded for it. So let me explain you step by step. So that may be helpful for you in future, for few of you, if you are working in the similar area, or if you are working with some processors where you find difficulty in maybe implementing the controlling algorithm, you may face difficulty in between. So how to proceed, or how to get this solution, the process I'm just going to discuss with you. Okay. So that was the introductory part, like what was the problem faced by us and what is the solution. I'll tell you at the end of this session. So we have just thought of not to implement our algorithm in DSpace. That was fixed. So then we started whether to implement it using a simple microcontroller or some microprocessor, or should we go for a digital signal processor. So that we are thinking of. Then we came to know that a processor will be basically doing two functionings. That is, one is data manipulation and the other is math calculations. So in some typical applications, we have like word processing or database management. You need to maintain spreadsheets, or you need to operate your operating system and all. So that data manipulation will be done by using this processor, and also it will help in mathematical calculations. That is, you will be processing the signal what you have. Some motion control and scientific engineering simulations, etc. will be done by using in this mathematical calculations. Like maybe you may include additions, subtractions, multiplications, divisions, and etc. Okay, but whereas here in data manipulation, the main operations will be like moving the data from one place to other place, or you may be copying data from one part to the other part. So these are the main operations in this data manipulation. So all the microprocessors will be performing both the tasks, like data manipulation as well as mathematical calculations will be done by almost all the microprocessors. But however, it will be a difficult task to make a device that is optimized for both. So this is very important point to be noted. Like every processor can do data manipulation as well as mathematical calculation, but optimizing for both is a bit difficult task, because some of the microprocessors are designed only for processing the data, or some of the processors may be designed only for mathematical calculations. So there are some technical trade-offs in the hardware design, such as the size of the instruction set and how interrupts are handled. So based on this, your processor will be depending, like whether it can perform data manipulation as well as mathematical calculations together in an optimized way. And here the other thing also, marketing issues you may have, like if you want to focus on mathematical calculations more, so it may be costing you more, or maybe like product lifetime also varies accordingly. Like here, in general, the digital signal processors are designed to perform mathematical calculations needed for digital signal processing. So this is a important issue where you have to consider. Here, data manipulation has given least priority, and mathematical calculations will be given higher priority specifically to digital signal processors. So that's why the microprocessor price is a bit lower when you compare it with digital signal processor. So these are few digital signal processors. So we have seen that in our control algorithm, we have a lot of mathematical calculations. Like for all the 5 phases, we need to do the PWM technique, also sense the VPV, IPV, and then give it to the ADC. Then from there, we need to operate MPPT, then PWM technique. So all these things should be taken care of. So for that, we have decided to use the DSP, digital signal processor, but not the microprocessor. So in this case, we have various options like TMS 320F 24XX, we have like 2412 or 2408 something, and TMS 320F 28 series was also there. So 2812 specifically we'll be using previously, but mostly it was obsolete now. So 2812 we cannot see in the market, it was obsolete. But rather we have 320F 2833X we have, like maybe 28335 in general. This will be using specifically for drive applications. So mostly for drive applications, this processor can be easily used. And we may also have C series processor with 6748 and so on. So C series in generally we'll use these kinds of processors in mostly communications or more electronic systems. But F series in generally we'll use for our drive applications. So C series we do not consider because it has more communication parts, rather focused on PWM signals and calculation, mathematical calculations. So these 3 are there for mathematical calculations, but however 2812 was obsolete, and why it was obsolete, that we will be comparing them. And 24124 is also obsolete kind of thing now, but only 28 series is there. So we just try to compare those things. So in this processor, its cycle time is 20 nanoseconds, where we can say the frequency of the processor is of 40 megahertz. But whereas for 2812 it was 150 megahertz, a similar frequency we have for 28335 also, that is 150 megahertz. This is your processor frequency. So cycle time we call it as in nanoseconds it was there. Like for each 6.67 nanoseconds it can have one instruction executed. So on chip memory we have here only 32 kilohertz and flash of 16 bits. But here it was increased to 128 kilohertz and same 16-bit flash memory. But whereas it was extended to 256 kilohertz with the 16-bit flash memory. So even in kind like memory kind of thing, it was having higher memory when compared to these two. Then coming to GPIOs, now you can see drastic change in these GPIOs, general purpose input output pins. So here you have only 40 individually programmable GPIOs, but it was extended to 56 in 2812, and again it was extended to 88 in 28335. So here you have a large number of GPIO pins. And coming to ADCs, actually this is 8-channel ADC is sufficient, but it has only 10-bit one. So for precision here you have 12-bit ADC in 2812 and 16 channels we have. The same 16 channels and 12-bit ADC has been carried forwarded to this 28335. So there is no change in it. Yeah, the most important, coming to PWM channels, here you have 6 PWM channels only. Here also you have 6 PWM channels. As we have discussed earlier, for 3-phase system it is sufficient. 2812 is sufficient for 3-phase system which can have 6 PWM channels. So independently you can generate 6 PWMs. But however, here you have only 9 PWM channels. And even in these 9 PWM channels, the dedicated 6 PWM channels are of EPWM and 3 are for HRPWM. Out of these 9 channels, 6 are for EPWM, 3 are for HRPWM. So you can again say only 6 are for EPWM, but this HRPWM can also be used if time permits, if If it is mandatory to use, that you can have. Okay, so this is one important point we just remember here, that it has only 9 PWM channels, and out of which 6 can be used for EPWM. Out of which 6 can be used for EPWM. Please remember this. And here in this 2812, you don't have any HR PWM channels. So only these are EPWM channels, enhanced PWM channels. Okay. Yeah. The major important point here again in these processors is about these two processors are of fixed point operation. They can do only fixed point operation. But whereas this 28335 can have floating point operation. This can have floating point operation. This is very, very important thing. Okay, so why it is important and what is the difference between this fixed point and floating point? Let us discuss. Okay, because when we choose a proper controller for our work to be done, we have to be sure, like for every operation what we need, whether the processor is giving that to us, or otherwise if processor is not capable of doing the work, then it is the processor what we choose, it will go in vain. Okay, so let us see what is the major difference between your fixed point and floating point. Like someone may say that fixed point do not handle decimal points. That is false. So it is false statement that fixed point do not handle decimal points. The decimal points can be handled by both fixed point as well as floating point. Fixed point processors do not only handle integers, they will also handle decimal points also, decimal numbers also, right? So, but what is the difference then? If this fixed point processor can handle decimal numbers and floating point can also handle the decimal numbers, then what is the major difference between them? The difference here is, in simple words, if we say, with a fixed point processor, the decimal point will be fixed. Okay, the decimal point will be fixed. But whereas in floating point, the decimal point can float or can be varied. For example, let us say if you want to represent a number 100.12 or 100, let us say for simplicity, it is simply 100, right? So you can represent this 100 number as 100.00, that's it. Or you cannot represent this in other way. But whereas in floating point processor, you can represent this 100 in such a way that you can have 10.00 into 10. Okay. Or 1.00 into 10 square. Right. I think now you understood. This is a fixed point. And these two representations are for floating point. Like 100 can be represented as 100 only, 100.00. This decimal point cannot change. But in this case, this decimal has now moved to here. Now again, this decimal point can also move to here. So the decimal point can be moved. So this can be achieved only by using your floating point processors, but it cannot be attained or achieved by using your fixed point processors. So what happens if you cannot move that? Okay, what happens if you cannot move that? What is the disadvantage with that? So you can see here, the floating point solves a number of representation problems. You can represent in various ways here, but whereas in fixed point, it has a fixed window of representation, only fixed window of representation, which limits it from representing both very large and very small numbers. Right. So this is what the major disadvantage with the fixed point. You cannot represent a very large number and very small number in your convenient way. Okay. And if you cannot represent this in such case, you will be losing your precision. definitely you will be losing your precision when you like do a mathematical operation of, let us say, two large numbers you have, and that two large numbers you are divided. So there the precision will be lost if you cannot represent these very small or very large numbers. Okay, this is the major disadvantage with the fixed point processors. Okay, but whereas in floating point you have a sliding window. So as I said, you can move the decimal point, so the window will be moved. So this allows the representation of numbers from, say, you can have many, like here you can see 12 zeros to up to what precision you can have. Many number of zeros after a decimal point, many number of zeros 1. So this precision you will be having by using floating point representation, floating point processors. And again, here you can have maximum precision. Okay, so this is the major advantage when you use floating point processor. So here again, like this is just a representation, how you represent, like as I have shown before, like sign you have, exponent, and then fraction. So here in floating point, you can represent it in two ways, single precision and double precision. So this is again a representation kind of thing in like in single precision, you can represent it a binary number in this way with 2 raised to 127. So which is like in double precision, you can have like twice the representation of this. Okay, so for example, again here I have shown like 50, the number 50 can be represented in these many ways. Okay, 50 into 10 power 0 directly, or 5 into 10 power 1, or 5000 into 10 power minus 2, 0.5 into 10 square, or 0.05 into 10 cube. So whatever the way you want to represent, 50 can be represented. The decimal is floating here. The decimal point is floating here. Okay, but whereas in fixed point, you can do the decimal number operations, but the decimal point cannot be moved. Let us say if you want to multiply 0.00238 with a number, say 0.00567. Okay, so whatever the answer you get here, you will be getting after a decimal point, you can represent it in only 5 numbers, let us say. So you cannot, but for this, after 5 numbers, you cannot know what is the digit you have. But whereas in floating point, you can move the decimal point over here. So something like if you have 1358 into 10 raised to minus 4, this can have here. You can move the decimal point. So precisely you can make the calculations. So this is what the major advantage with the floating point processors. So to conclude this floating point and fixed point, you can generally say that the production cost of fixed point processors is very, very less. So that's why when we compare 2812 with 28335, people say that 2812 is sufficient. It was sufficient for a very low cost systems, but whereas when 28335 was introduced, it has overtaken all the drive applications from 2812, since it is having floating point processing, but not the fixed point. Here precision, range, so development time will be very less here. So since it has like frequency is same for both 150 megahertz, but still people prefer 28335 since it has floating point kind of operation. And also you can have 9 EPWM channels, but still 6 are only useful when you compare with 2812. Right. So now when you just move ahead, this is just a representation kind of thing in multiplication. Fine. Yeah. Coming with TMS 320F 28335 processor. So this is the processor box what we have. You can see this is the processor what you have installed, and this is a DSP was made by some other like TMS. This was supplied from TI, Texas Instrument, but whereas The development board, which should have its accessories and all, that will be developed by like it is said as EZ-DSP when you develop this processor into a useful board. So in this processor you have different pin configurations like USB connector, which can be directly connected to your personal computer or computing system, and power supply will be given to this. So mostly it would require like 3.3 volt or 5 volts power supply. So that will be given to this through the adapter. And yeah, this JTAG interface is must and should for any processor. And this JTAG will be interfacing your PC with the processor. So it is like a medium or mediator between your PC and the processor. Yeah, someone want to say something? Okay. Yeah, so we also have analog interface here. The important parts I'll tell you. This is the analog interface. You can see P9 as analog here. So where you have these pins connected to the ADCs of your processor. So these are connected internally with ADCs of your processor. And then you have GPIO pins, IO interface you have. So these are all the GPIO pins which we have. So in this again it is categorized like P4, P7, P8. So these are the categories of your GPIO pins. So this is also important thing to know which pins we should use out of this P4, P7 and P8 because arbitrarily you can't use any like pin. It should be dedicated for some particular operation. And here you have like P10 and these pins are for expansion, future expansion purpose. So they are not configured to any IOs, but here P4, P7, P8, they are configured to specific purpose. Okay. So let us see which pins can be used. So as I have shown you P4, P8, P7. So these are specifically used for IO configuration. And analog interface you have P5, P9 as I have shown you in the previous slide. So other things are like for communication purposes, these are for communication purposes. And for expansion P2, P10 are left. Okay, P1 is for JTAG interface and this J201 is for embedded JTAG. So these we do not use. So our point of interest is in this analog interface. Okay, this is ADC pin directly. So our point of interest is in this P4, P8 and P7. So let us see what is there in that P4, P8 and P7. Okay. So if we go with the P4, P8 and P7, here the numbering you can see from 1 to 20 pin you have for P7 and for 1, 2, 3, 4 so on up to 40 pins for your P8 and 1, 2, 3 so on up to 20 pins for P4. Okay. So in this, this table is shown for P8 specifically. Okay, this table is for P8 where you have 1, 2, 3, 4 so on up to 40. So here this will be 3, 4, 5, 6, 7, 8 so on up to 40. Okay. So in this if you observe the GPIOs which are dedicated for EPWM specifically because our application needs EPWM. So here if you observe EPWM 1A is of 9th pin, EPWM 2A is 11th and 3A is 13th. So 9, 11 and 13. So these three pins we have EPWM 1A, 2A, 3A. So which can be used for top switches. And similarly if you see GPIO 1 that is EPWM 1B that is 10th pin 2B and 3B 10, 12, 14. So these 10, 12, 14 these three are for 1B, 2B, 3B that can be given to bottom pins. Okay, 1A represents first leg. 1A represents for first leg top switch, and 1B represents first leg bottom switch, and 2A represents second leg top switch, 2B represents second leg bottom switch, so on. So here we can see 1A, 2A, 3A and 1B, 2B, 3B. But as we said, 6 channels are dedicated for EPWM. So here we have discussed only 3 channels. Okay, only 3 channels, that is 1A, 1B, 2A, 2B and 3A, 3B. So you can see 4A also. So the 16th pin you can observe, it has EPWM N4A. Okay, this 21st pin also has EPWM 4B. Right. Even if you see, EPWM 5A is here for 30th pin. Okay, and 5B is here for 31st pin. 6A is for 32nd and 6B is for 29. So these are randomly placed. But however, you have 1A, 1B, 2B, 2A, 2B, so on up to 1A to 6A and 1B to 6B. So total 12 GPIOs, total 6 channels, 6 PWM channels dedicated for EPWM, and in 6 PWM channels you have 12 GPIOs. So as we have total 12 GPIOs here, so this is not sufficient in our case because we had total 20 switches, and this can generate 1A, 2A, 3A, 4A, 5A, 6A. So 6 independent firing pulses. 6 independent pulses. And other 6 are their complementary. Other 6 are their complementary. So only this we have. But in general we can use 12 GPIOs. So this is the pin description in general, but how we try to handle this, let us discuss in detail. So let us discuss something details about your enhanced PWM module. So in this enhanced PWM module, like you have enhancing in deadband resolution when you compare with simple PWM pins, and enhanced interrupts you have, because interrupts should be with respect to your interrupts should be with respect to your ADCs, and if you have any other interrupts like counter interrupts, so that can be taken care. So interrupts enhancement is also there in this, and high resolution period capability PWM pins are also there, like HRP PWMs. So, but in general, EPWM we use generally this HR PWM can be used for high frequency DC-DC converters, but not for inverters. And digital compare sub module is also there, like you have event triggering and trip zone sub module. That sub modules let us discuss in detail. So I'll discuss this point when you discuss the sub modules in detail. So in total you have 7 sub modules in a EPWM module. So in EPWM module, when you implement, in total you have 7 sub modules. So first sub module is your time base, then counter compare, action qualifier, deadband, PWM chopper, event trigger and time trip zone. So out of these 7, very important for a person who are implementing the inverter control. So time base is very important, counter compare is very important, and more than that, action qualifier is important, then deadband module is important. So out of 7, these 3 are very essentially studied in detail. Others, okay, they can be said default, whatever you have, that can work for you. And EPWM module can communicate with various things available in the processor. So a single EPWM module can communicate with your trip zone initiation, or it can communicate with your ADCs, and it can communicate with your synchronization signals, input synchronization, output synchronization. This synchronization can be used to synchronize with other EPWM signal modules. So this communication is done to other EPWM module. So why we need communication between one EPWM module to the other EPWM module? It is very simple. Like if you want to implement inverter, the phase shift should be maintained for 3 legs. So one EPWM module generates 1 pulse per 1 leg, or it can generate 2 pulses per the leg, both top and bottom. But however, if you want to implement the next leg pulse, so the next leg pulse, like this is 1A, 2A. So 1A, 1B will be generated by EPWM1, let us say. And 2A, 2B will be generated by EPWM2. But however, there should be proper phase shift between these two phases. And that can be maintained by enabling this synchronization. Okay. And peripheral bus you have for other communication purposes. And yeah, importantly, the output from here is your EPWM-A and EPWM-B. So both top and bottom switches firing pulses can be generated from this, which can be given to your GPIO MUX multiplexer. Okay. So let us focus on the important submodules of EPWM module. As I said, the synchronization will be used to communicate with the other EPWM modules. Like say here EPWM1, EPWM2, EPWM3, so on up to EPWM6 you have. So first EPWM like 1A, 1B generated here, 2A, 2B generated here, so on up to 6A, 6B. Okay, that can be synchronized by using your synchronizing pins. Okay, so let us see the submodule connect. So all the 7 submodules, whatever you have, that are shown here, like everything is interconnected and they have their own functioning. But I do not want to discuss this detail here, but block by block let us see so that it will be clearly understood. So first block, let us see like time-based submodule. So in this time-based submodule, you have various registers, and those are like time-based control register, time-based status register, time-based phase register, and time-based counter register. In addition, you have time-based period register and HRPWM extension phase register. So if you want to use only HRPWM pins, then only it is used, otherwise it has no use. But mostly used are time-based period register, time-based counter register. These two are mostly used for implementing any PWM technique, So what is the purpose of this time-based module? Time-based submodule will specify the time-based counter frequency. So here this is very essential, like time-based counter will be giving you the frequency or period of the control, how often it should occur, how often event must occur. So that means it will be defining the time period. Okay, that means in our language, if we wish to say, it will decide the switching frequency of your inverter. It will decide the switching frequency of the inverter. Okay, so if your counter value is equal to period, this period value is nothing but your inverse of this period will give you your switching frequency. Okay, period means it will be in time, converted in time, and 1 upon conversion of period into time, that will give you the switching frequency. Okay, so this is most important. The time-based submodule will be giving you the information of switching frequency, and you can generate the reference waveform for your PWM signal by using this time-based submodule. And the reference waveform can be a sawtooth waveform with up count, or a sawtooth waveform with down count, or a triangular waveform. So in various forms you have your reference waveforms for PWM technique, right? So this can be having in a up count mode, or down count mode, or up down count mode. So up count will generate this, down count will generate this, and up down count mode will generate triangular waveform. And that time period of that will be calculated like this, with TB period value plus 1 multiplied by time-based clock. And time-based clock, we can define it in the program. So we can set it in the program. and inverse of this TPWM will give you the frequency, that is the switching frequency. But whereas for this formula applies for both up count and down count, but whereas for triangular waveform up down count mode, it will be like 2 into TB period into time based clock. Okay, so for example, let us say if you want to generate a 1 kilohertz triangular waveform, what should be the value of time based period? That you can just calculate by using the above formula. So you should generate a triangular waveform. That means up down count you need to use, and its switching frequency should be 1 kilohertz. So 1 kilohertz it should be. So for that, so system clock frequency is 150 megahertz, as we have taken it for 28335. It is fixed. HSP clock division, this is high speed clock division. Actually, this will use it for prescaler, as a prescaler. Prescaler means how I would explain. Let us say you have a 150 megahertz processor. This 150 megahertz processor, you can use it as a 75 megahertz processor also, or you can use it as a let us say like 15 megahertz processor also. If you divide this system clock frequency with 2, then it will become 75 megahertz. If you divide this with 10, then it will become a 15 megahertz processor. Okay, this is just a prescaler. That means for precision, if you whatever the switching frequency you use, so for that switching frequency, to improve its precision and resolution, we use this prescaler. So as we are dividing it with 2, so it will become now system clock by 2 into 1, that is 75 megahertz. So time based clock will be now 75 megahertz, and time based clock inverse you can have, that is time of this time based clock value. So TPWM is like 1 upon 1000, which is calculated from here. So we want 1 kilohertz. So for that TPWM will be 1 upon 1000, that is 1 kilohertz. So it should be 1 millisecond. So TPWM will be equal to 2 into TB period, that what we have. So TB period value calculated from this is 1 millisecond by 2 into this time of time based clock. So that you get count as 37,500. So when you give input as 37,500 as TBPRD value, and you put this in the TBPRD register, then it will generate 1 kilohertz switching frequency. So this is how you calculate the switching frequency, and you can generate precise switching frequency from the processor by this proper calculations. Okay, next coming to counter compare register. This is not much useful, but it can have only one operation. Like this is used for generating top pulse as well as bottom pulse. So you can have compare A and compare B. So that values you can have. That means when you have a triangular wave and you have some reference wave, some say sinusoidal reference wave. So this is say for phase A and some for phase B, let us say. So this can have like compare A value, and other reference wave can have like compare B value. So it is, this time base is for generating triangular waveform with some switching frequency Fs, and this is for generating reference waveform, let us say, reference waveform. Okay, that compare value you can give here. Then comes action qualifier. This is most important thing, action qualifier. Okay, so here in this action qualifier you will be deciding like with what operation you want to generate your switching pulse. So you want to like compare this comparable value with like less than or equal to, or greater than or equal to. Like sometimes you will generate PWM pulse, like if sine wave is greater than your triangular, then generate the pulse as active low. or if sine wave is less than your triangular, then generate the pulse as active low. Or sometimes if sine wave is greater than triangular, then generate the pulse as active high, or here active high. So whatever be the logic, here the comparator logic will be implemented in this action qualifier. The comparator logic will be implemented here. So that is done by using this action qualifier, and it is very, very important to know about this action qualifier. So yes, so here the purpose of action qualifier submodule is it will do three operations. One is set, clear, toggle. So generally, as I explained you, in case of simulation, what we do, like we'll take a sinusoidal waveform as reference wave, then we'll generate triangular with a random signal generator, and we give it to a comparator. Less than or equal to or greater than, we'll give it to a comparator, and that comparator will give me the pulses output. So with the various variable pulse width modulation, as you increase or decrease the amplitude of this sine wave, so your modulation will be changing over here. So this actually we do it in the simulation, but whereas coming to the processor, it has its own language. So we need to understand its own language. So here we have set, clear, and toggle operations. So when we use this, like let us say, if your counter value is equal to period, so period means, let us say in triangular waveform, as you generate like this, so this is termed as 0, counter is equal to 0, and here the peak value, where here counter is equal to your period, PRD. So we have defined this period for specific switching frequency, as we have seen earlier. Okay. So when counter is equal to period, the time base counter equal to the period value, that is TB-CTR is equal to TB-PRD. So whatever the value we define in this register, now this is copied into this register. Okay. So if counter value is equal to 0, it will be equal to 0. In this register, it will store directly 0. So if counter value is equal to a compare A, then this register will be having the value of compare A. If it is equal to compare B, this is having the value of compare B. That means this time-based counter can have values of both the carrier waveform as well as reference waveform. It can handle both the values of carrier wave as well as reference wave. From this you can see. So this is for carrier, this is for reference wave, right? And managing priority when these events occur concurrently. So priority wise it can handle. Okay. And it can provide independent control of events when the time-based counter is increasing and when it is decreasing. So let us say if your carrier waveform is this and your reference waveform is this, let us say this has some compare A value, and it can have independent control, like whether when you have counter is equal to compare A value, when this counter is equal to compare A value, you need to generate either active low or active high. Okay, so this can be independently done by using this action qualifier, and that is done by using set, clear, toggle operations. So how this set, clear, toggle will be used for implementing this greater than, less than, or equal to operations. Okay. Yeah, here you can see how this will be used for greater than, less than, or equal to operations. If you set high, then set output of EPWM A or B will be high level. So it will be set to a high level. If you say clear, if you use set, it will be going to high level. If you say clear, it will be going to low level. That means if you say set from 0, it will go to high level. If you put clear, it will be from high level to 0. So set operation will give you a rising edge, and clear operation will give you a falling edge. Right. And toggle, here you have if EPWM A or B is currently pulled high, then pull the output low. And if it is currently pulled low, then pull the output to high. That means it will be toggling. If it is low, then it will pull to high. If it is if it is low, it will pull to high. So it will be just toggling in between these two. If you have low, then it will make high. If it is high, then it will make low. This is the toggle operation. And do nothing is there, but in general we don't use. If you use do nothing, it will keep at the same level. That continuously, if it is 1, continuously 1, or continuously 0, it will be 0 only. So it will do nothing. So these are very important, like set, clear, and toggle operations to attain the PWM pulses.
May I interrupt?
Yes, yes.
I have the same logic.
Yeah.
I'm starting controller. At that time, I'm having some echo.
Excuse me, like your voice is not so clear. It is breaking in between.
Yeah, now it is audible, sir.
Yes, yes, now it is clearly audible. Yes.
Okay, so basically, what I was facing the issue, the moment I used to start the controller, one pin used to be high, one pin used to be low, right? Because that is how the logic of inverter goes. But initially, while starting the very first time, I want all the pins to be at low state, which was that is something what I was not able to attain.
Okay, okay. I'll address your doubt in the future slides where I'll explain you program.
Sure.
I have a C program written to it. So in that
Sure,
program,
sir.
I'll explain you. Okay.
Thank you so much.
Yeah, yeah. Okay. So going ahead. So this is some example how you can generate the firing pulses by the comparison value. Okay. So let us say you have for single edge only up counter you have used, and it is a single edge asymmetric waveform. So you have only falling edge delay. You have only falling edge delay here, falling edge here, and you have independent modulation for both A and B, let us say. So this is some waveform of reference for compare B, and maybe this is some waveform for compare A, let us say. So here they can be independently controlled. If you see here the action qualifier for A, bit 0 it is written, and when it attains 0, action qualifier should set. When it attains 0, that means 0, if I write here, that means CTR should be equal to 0. Time-based counter value, whatever I have, this time-based counter should attain 0. So when the program is executed, so this is your 0 and this is your peak, that means time-based period value, and time-based counter it is counting. So when it is attaining 0 at this point, 0, then it is saying that you should set. Set means from low to high. So it has set from low to high. A is set from low to high. Right. Then next again what it is saying, action qualifier for A again, CAU. CAU. A defines for A register and U defines for up count. This defines for up count. So when the counter of A register is counting upwards, so when TBCTR is attaining the value of CAU, then it should clear. When it is counting upwards. So now it is counting upwards from here, right? So counting up, counting up, counting up. And when it attains the value of CAU, which is here CMPA, that is compare A. CMPA. So when it is attaining this, now it is saying that clear. That means when TBCTR is equal to CMPA, it is now clearing. It has now cleared. So this is how you generate firing pulse for A. Then again, when 0 is attained, it has set. When CMPA is attained, it has cleared. So here it is set, here it is clear, here it is set, here it is clear. So in general, what you say when you use in simulation, the reference waveform is if it is less than your triangular. If reference is less than triangular, then generate high, then generate pulse. In this case, right? This was the logic when you use simulation. Then you generate 1. So if reference is greater than triangular, then generate 0. So if reference is greater than your triangular, generate 0. Okay. So this is for every switching frequency. So every switching time period, this is total switching time period, TPWM. Right. Similarly for B. So for B, action qualifier is set clear. So at 0 it is setting and it is clearing at compare B value, CMPB. So this up count is very essential when you are using for generation. Why? Because by using time base you have generated up count. So if you do not write U, it won't execute this particular command. Okay. If you write CBD here, it won't execute this command because you don't have any down count counter. You are using up counter, you are not using down counter. So CBD can be used only when you use down counter. For example, okay, here there is one more thing. Upper one we have seen for active high, you are setting then clearing. Inversely you can have active low. That means when it is at period you make it high, when it is at 0 you make it low. So it is just inverse operation. So only clear set, here previously was set clear. So only this command will generate you the completely complementary pulses as previous one. For example, if you have up down counter both, so you have generated the time based generator as used for generating this triangular wave, but not this sawtooth wave which we have seen earlier. So in this case again, you can see here. Now here you don't use 0 or TB period value, but you use up count and down count mode. For A register, your counter is counting up. So when you attain CMPA value, then it is setting. That means low to high. And when it is down counting, so from period to 0 down counting, when you attain CMPA again A, but down counting, then you clear it. Okay. Similarly for B register, for up counting you set, for down counting you clear. The same thing you can do it in reverse way. Like when you are up counting, you can write action qualifier clear. Okay. So if you are here for down counting, you can set. If you write this kind of command, so what happens when it is attaining here, you are saying that clear. That means previously it was high. Then at this point you have cleared. Then at this point you are again setting. Then at this point you will be having continuously like this. So this is the waveform you get by using this command. That is just by shifting one command up down. So this will happen. Okay. So this is how you can generate firing pulses. Again here, yeah, this is one more thing. You can toggle them like if you want complementary pulses, for A you want in this way and for B you want in complement. Okay, complementary pulses, you write up count set for A and down count you clear. For down it is clear. This is fine. But inversely you can do for B. For up count you are clearing. So for up count it is clearing. Whereas for down count it is setting. So these two are now complementary pulses. So this is very useful in generating dead time. For dead time. So in general for all the inverters what you use, so those inverters will be using this kind of sequence in action qualifier so that you can have dead time in between these two. Okay. So now we can discuss with respect to dead time. So dead time again very like simple to understand. You can have dead time between two pulses with a rising edge delay or falling edge delay. So this is the formula to be calculated for a dead time. So if you want rising edge delay, then in deadband register you have rising edge delay value multiplied by your time of time based clock, and for falling edge delay you have a register with deadband for falling edge delay, and you can have time of time based clock. And again, very important to know here is you can have independent rising edge delay and falling edge delay independently. That means it is not mandate that rising edge delay should be equal to falling edge delay for anything. It can have independently. See here in first case you have only rising edge delay, there is no falling edge delay. In second case you have only falling edge delay, you don't have any rising edge delay. This was the original signal. So you can have active high complement. That means you have rising edge delay as well as falling edge delay for complementary pulses. You have active low complementary also. So both are like active low and active high, both active low both. So these kind of things you can have by using these commands. So in general for inverter we use active high complement. In general for inverter we use active high complement, because here you have top switch and bottom switch. So top switch is turned on, let us say. So in this case you should not turn on your bottom switch. In active low it is happening, so this is turn on, this is also turn on. So this should not happen. But whereas in active low, active high complementary, when the top switch is off, this is for A and this is for say B, 1A, 1B, let us say. So when this is off, this B is also off. Okay. After turning this B switch completely off, then only you are turning on your A switch. Similarly here you can see, when this top switch is on, immediately you are not turning on bottom switch. After this switch is completely off, after this time delay, like after falling edge delay, you are turning on your B switch. So this is the delay very essential for an inverter leg. So that's why in general for inverters we use active high complementary. So these are some calculations for rising edge delay and falling edge delay calculation. Like it also depends on the system clock frequency or the prescaler, what I said. Like when you divide it with a prescaler, the delay will be changing. So for that sample calculation I have given here. Like let us say for the same signal which we had earlier, if you want 2 microsecond deadband with a falling edge delay. So in that case you can calculate by using these calculations, like time based clock you have, time of time based clock you have, and time based clock value, and delay is given as 2 microseconds. So 2 into 10 raised to minus 6 divided by this time of time based clock which you have calculated by using your prescaler. So here the deadband for falling edge delay, define it as 75. So like in previous case 37,500 you got it for a time based period. So in that if you want to give a delay, so maybe like 75 or 150 you can have here. So which can vary your dead time. And PWM chopper, this is not much essential because it will be just giving you high resolution pulses here. Okay, this is just chopping the pulse, even the pulse what you have generated. Generally, we will use it for high resolution EPWM signals. And trip zone, yeah, this is for protection purposes. So you have trip zone control, like as you interrupt in between, if there is something gone wrong with the pulses, and if you want to trip the entire circuit of the processor, that you can do by using these registers, trip zone registers. Generally for protection purposes this will be using. And yeah, event trigger, this is most important again. All the events can be organized in a way based on the priority. that will be done by using this event trigger or interrupt register. I won't go much deep into that. Yes, this is a very important thing I want to discuss you. Here, this is the program which can be written in Code Composer Studio. So in CCS, the Code Composer Studio, which we use for programming the DSP. So it uses the simple C language. The Code Composer Studio will use simple C language, and in that we have used, we can write this kind of program. So here you can see section by section. This is written in EPWM sub module actually. So it is a part of the program but not complete program. This code is just for EPWM sub module. Before that you need to define the EPWM pins and all that you have to define. So in this, as I said, first time-based period, which we define it as 800, let us say. Okay. So where that period will be like counting for twice, like 1600 time-based clocks. And phase shift, we do not have any phase shift here. I'll explain this phase shift later, because if you have two signals to generate, there you need to have phase shift, like to synchronize both EPWM channels. Counter mode, yeah, this is very, very essential to generate the triangular waveform. Counter mode, if you write time base count up down, it will generate a triangular wave. If you write here time base count up, then it will generate ramp like this. If you write time base count down, then it will be generating the like this. So you can have three various triangular waveforms or carrier waveforms based on this command. Then phase enable, now it is disabled. I'll show you when you enable the phase, how it will be operating in the next slide. Here shadowing, we generally avoid this shadowing, but it is by default set. And then synchronizing downstream module, that is EPWM module 1 with synchronizing with EPWM module 2 when the counter counting 0. This you can synchronize at any part, like when time base counter having a value of period, then also you can synchronize, or time base counter at compare A, then also you can synchronize, or at compare B, then also you can synchronize. So you can synchronize at whatever part. You can have it 0, or you can have it period, or you can have whatever the way. Then you will be loading this value. Actually, these shadows will be using like cache memory in your PC, just like a cache memory. Like event to event, that should be taken forward. So previous value will be saved as this shadow. Then it will be carried forwarded. So that will be loading your counter value. Okay. The most important is your action qualifier now. So in this action qualifier, for compare register of A, up count, while counting up you are setting, and while counting down you are clearing. Okay, then deadband is fully enabled, and active high complement. We are using active high complement, and deadband falling edge delay of 50, rising edge delay of 50 is given, and compare a register, it has stored as 500 value. Right, TB period is of 800, compare is stored as 500, deadband of 50, 50 is given, active high complement it has said, and it is set at up count and clear at down count. So based on this, you can draw the waveform. So you can see from 0 to 800 it is counting, from 800 to 0 again it is counting, so that I told total 1600 counts it has. Then in rising edge delay, you have 500, at 500 it will have for 50. So for 50 count, so this is up to 50. Like if you can plot here, so this will be 550. Okay, active high complement you used. So because of that, it is high, it is low. Active high complement it is generating. At 500 again here, you will generate, but at 450 it will generate the delay up to here. Okay, so this is the code when you use active high complement with triangular waveform. Let us see how to enable the phase. So when you enable the phase, Like for second register, you can only change these two. Here you have EPWM1 register for A and B, right? For second EPWM module, you can just change these two and you can enable the phase, remaining everything will be same. Enable the phase and you make synchronize with above. Just synchronize with above. Okay. So that you have enabled the phase and it is synchronized with above. Let us see. This is the same thing, but okay. Here I have changed, period is same, but I have changed compare a value to 600. If I have changed compare a value to 600. So compare a value only changed to 600, other things are same. From 0 to 800 it is counting. Okay. And it is synchronizing with above, so that your phase here got as 0. So 1A, 1B, this is 2A, 2B, second register. Okay. So this is what done. Now coming to the solution which we want, that is I need to generate, I have in total I had 1A, 1B, 2A, 2B, 3A, 3B, 4A, 4B, 5A, 5B and 6A, 6B. So 6 channels, 12 Gpios, but I need to generate 20 firing pulses of 5-phase open-end winding induction motor. So what I have done is I considered only top switches of dual inverter, 1, 2, 3, 4, 5 of top switches, 1, 2, 3, 4, 5 of second inverter. But bottom switches I generated by using a delay circuit externally. So I reduced my 20 pulses to 10 pulses now. So these 10 pulses should be generated independently by using this 12 Gpios what I have. So for that even 2 are extra, so I excluded these two. So I have 1A, 2A, 3A, 4A, 5A. Why can't I generate independent pulses for 1A, 2A, 3A, 4A and 5A? This is done already, but can I generate independent pulses of 1B, 2B, 3B, 4B and 5B? This was the question, right? So 1A to 5A, I can give it to first inverter, this is done. But if I can generate 1A to 5B for second inverter top switches, till now we have seen that this is for top switch, this is for bottom switch. But if I could generate by using this 1B to 5B for top switches, is it possible in the processor? So this is what we have planned to do, and successfully we have implemented that. We have changed the code such that these pulses are not generated for bottom switch, rather they are generated independently from this 1A. Now 1B is independent of 1A, 2B is independent of 2A. Okay, that we have done using this command, that whereas they can be generated complementary with independent comparison of A and B. So independently we have generated and given it to, now this A is given to like first inverter, B is given to say second inverter first switch, but they are not bottom switches. So this we have done by using the 28335 processor. Okay, so this is how our journey was when we had a problem in implementing the processor and firing pulses to dual inverter, specifically 5-phase dual inverter with 20 switches. So we have studied this and we successfully implemented, and the hardware results are there already published in the transactions. So you can refer my papers for that, or you can contact me at any time with the contact email and number given on the screen. And yeah, thank you very much for patience listening. And if you have any queries, please let me know. And I think the question asked before in between, it was answered in previous slide. So how to set it 0 initially, right? If you want to set both these 0 initially, then you need to change only the action qualifier. You need to change only the action qualifier. This is the solution. So change action qualifier accordingly such that you can get both zeros. You will get both zeros. So when you define your counter A up or counter A down based on the set, clear or toggle, whatever it is, you can define that. Yeah.
Yes, sir, that's very true. But I initially want to make it set clear at first.
Yes.
Hello.
For that you can have a loop, like say for n is equal to 1, I is equal to 1, you make it a separate code.
Okay.
And for I greater than 1, you make it another code.
Got it. Thank you, sir.
Yeah. Yeah. Any more queries?
Thank you, Dr. Ramsha Karampuri. There is one question in the can be implemented between PWM 1 and 2.
Pardon?
How can phase shift be implemented between PWM 1 and 2?
Yeah. Phase shift, here I have shown you. Phase shift is, here phase is enabled here. So when you enable the phase, previously it was disabled. Yeah, previously here it is disabled. So if you enable this phase and give the synchronization value here, so here you can see synchronize in. So if it is given as time-based sync in, it will be synchronizing with the previous one. Otherwise, if you want to give the phase shift here, you should define some time-based counter value and that value should be entered over here. Like we have entered for compare as 600, then that calculation must be done. So how much phase shift you want to give, accordingly you have to enter the value here.
Hello, good afternoon, sir.
Yes.
Actually, I am asking this question about this phase shift. As you already mentioned that the TB sync in that should be changed into some numeric data. Accordingly, what amount of shift I need? Is it?
Yes.
Okay. Okay, sir. Okay. Thank you, sir.
Yeah. Thank you. Any more queries?
Any other participants? Yes.
Okay, if there are no queries, then I think we can conclude. And yeah, every time when I conclude, I'll say that be busy to make your life easy.
Thank you, Dr. Ramsha Karampuri, for explaining all of the work that you have done about implementation of parliamentary systems in DSP for application, and also for explaining the DSP 28335 in sub modules and RAMs. Thank you so much for accepting our invitation, delivering a talk or delivering a session during our FDP. Thank you.
Yeah, thank you, ma'am. Thank you very much.
Dear participants, I request once again that there is a validity function in the afternoon at 2:30 and followed by a test. Also, the test duration is 30 minutes. 25 questions will be there. And the questions will be covering all the sessions, all the 14 sessions. So see you at 2:30. Thank you. Thank you, Dr. Ramsha.
Yeah, thank you, ma'am.
Thank you all participants.
Ma'am, please download the attendance. Mini, ma'am.